So this little video is about convergent series. Well, it's about convergent series and divergent series. So what I'm talking about is series where you sum an infinite number of terms, but each term in the series gets smaller than the previous term. And the question is whether or not they come to a finite total, or whether the total gets bigger and bigger and bigger the more terms you add. Well, the total does get bigger and bigger and bigger the more terms you add, but it's whether the limit of that sum is finite or not. So let me give you an example. It's the easiest example in a lot of ways. 1 plus a half plus a quarter plus an eighth, and so on. So I'm halving each term to get the next term. Okay, and the question is, what does the sum eventually equal? Does it equal infinity, or does it come to some finite sum? And the answer is it does come to a finite sum. It comes to 2. Okay, and the way I like to think about it, to see that that's the answer, is I imagine a length, a ruler or something like that, that measures exactly 2 in length, and I cut it up. So I cut it in half, so this half measures 1, and I remove that half and put it down here. So now I've got 1 here. And then with the remaining unit length here, I cut that in half again, and I take this half and I move it down here. So I've got 1.5 now. And then I take this one and I cut it in half again, and I remove that half. So that's a quarter. So I've got a 1 here, a half here, and a quarter here, and there's the remaining quarter up there. Okay, and I keep cutting that in half. So I've got an eighth now, and an eighth here. So can you see that what I'm doing is I'm building up this, I'm taking smaller and smaller chunks out of this and moving them across. So this thing's getting bigger and bigger and bigger, but it's never going to get to be equal to 2, but it'll get very, very, very close to 2 as I cut thinner and thinner slivers off there. So that's my way of seeing that the limit of this series, it gets closer and closer to the value, it gets arbitrarily close to the value 2. Okay, so here's another series where it's harder to see what the sum might be. And sometimes it's good to go with your intuition on these things, and then spend a bit more time thinking about it a bit more carefully and see if your intuition is correct or not. Some of these are easy to prove, some of them are hard to prove. Okay, so what about that one? Well, the answer with that one is that it diverges, although the terms do get smaller and smaller as you go along, and all of those terms are actually included in here. This sum actually comes to infinity. Okay, and it's not too hard to see. The way that you see that is you look at well, you look at these, let's take the 1, okay. Now take this term here, which is a half, so we've got 1.5, and then take these 2 terms together. So what's the value of those 2 terms? Well, I don't know exactly, but I know that this one is a quarter and this one is bigger than a quarter. So whatever it is, it's bigger than a half. So we'll add a little bit there. And now let's take the next 4 terms. Well, again, I don't know what the value of the sum of those 4 terms is, but I know that this one is an eighth. So this one is an eighth and a little bit more. This one is bigger again, and this one is bigger again. So we've got 4 things that are bigger than an eighth or equal to an eighth. So that must be equal to a half plus something as well. So what happens if I take the next 16 terms? Well, I could write it out, but I'm sure you see the pattern now. So the answer is that the next 16 terms will give us another half plus some little bit. And the next 32 terms will give us another half plus something. And the next 64 terms will give us another half plus something. So I can get to any value I want. I can get to 1,000,000 here if I'm prepared to go to 2 to the power of 1,000,001 or something terms. So I can get an arbitrarily large value by just counting enough terms, because I can always find enough terms to give me another half. I just keep going. I might need an awful lot of terms, but I can get to any value. So this series diverges. Okay, so now come to the really difficult ones, and they're quite counterintuitive, I think. So here's another one. Supposing that we take just the reciprocals of the primes, 1 over 3 plus 1 over 5 plus 1 over 7 plus 1 over 11 plus 1 over 13 plus 1 over 17 is the next one, isn't it? 1 over 19 and so on. What about that one? Does that converge or diverge? Well, there's certainly a lot of terms that we start with, so we're getting, quite a considerable value quite early on. But then we do know that the primes become more and more sparse. So once you get up into the hundreds and thousands, it's a pretty it's a pretty bleak world, really. There aren't very many primes. Occasionally you get 2 primes right next to each other, or almost next to each other, but the gaps are pretty big on average. In fact, the average gap, I think, once you get up to a value of n, like 1,000,000, the average gap is something like log n. So, those terms are going to be few and far between. But the fact is, it diverges. You can find a proof on the internet. I'm not going to show it to you because it's too difficult. But the fact is that one diverges. So here's another one. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. I'm going to 1 over 8, 1 over 9, 1 over 10, plus 1 over 18, plus 1 over 19, 1 over 20, plus 1 over 89, plus 1 over 90, plus 1 over 91. Okay, so I'm writing them all out, but I'm leaving a few gaps. What you do this time is you erase anything that's got a 9 in its decimal expansion. So, decimal representation. So we'll take away that one, we'll take away that one, 19, we'll take away 89 and 90 and 91. In fact, we'll take away all the 90s, so the next term will actually be 100. And then we'll go start counting them again, 101 and so on up to 108. Then 109 will get missed, 110, 111, 112 and so on. Once we get up to something like 900, we'll miss a whole great bunch of them, but then we'll be back on 1 over 1,000, 1 over 1,001, 1,002 and so on. So the question is, does that one converge or does it diverge? So the answer is that one converges. And that's really surprising. Well, it surprised me, but I don't know. The reason it converges is because nearly all numbers have got 9 in them. So this is it's a really good example of something called the strong theory of small numbers. If you just look at the first few numbers, if you just look at the small numbers, you get misled. You get the wrong impression. You get the impression that 9s are actually quite thin on the ground when they aren't. 9s are actually really thick on the ground, and once you get up to considering all the numbers between 1 and, say, 10 billion, you find that nearly all of them have got a 9 in it. And, another kind of intuitive way to see that should be true is, base 10 is an arbitrary thing. We're told that we counted base 10 because we've got 10 fingers. So, other types of people could count in other number bases, and in fact, in some cultures they did. So computer scientists count in binary, and so that's base 2, where everything is a 1 or a 0. Okay, so you write a number out in binary, well, we've got 0, 1, then for decimal 2 we write it like that, decimal 3 we write like that, decimal 4, decimal 5 we write like that. Now, imagine that you write out all the reciprocals in binary and strike out the ones that have got a 1 in them. Well, you know, look at this. Pretty much every number's got a 1 in it. Apart from that one, every other binary number's got a 1 in it. And how many binary numbers have got a 0 in them? Well, not every one, but nearly every one. Let's go on a bit. Yeah, okay, so there are some binary numbers that haven't got any zeros in, but they're pretty few and far between, and so that might help you to see that actually most numbers contain most of the possible digits.